In section 4.1, we talked about basic probability rules, specifically when it comes to one event. In section 4.2, we're going to go a little bit further than that with more than one event, what's called compound events. So just like a compound sentence, compound events are just usually more than one event. And also similar to compound sentences, we're going to join those probabilities together with either a conjunction like and or a conjunction like or. So we'll talk about all of that in this section here. So we'll start with conditional probability and multiplication rules. So let's say that you roll 2 dice. The question is, what is the probability that you'll get a 5 on each die? And then also consider a collection of 6 balls identical in every way except in color. You have 3 green balls, 2 blue balls, and 1 red ball. You draw 2 balls at random from the collection without replacing the first ball before drawing the second. What is the probability that both balls will be green? How are these two examples alike and how are they different? Well, they're alike in that you're considering a probability of 2 events happening, right? In the first example, the first event is getting a 5 on the first die. The second event is getting a 5 on the second die. And it's similar to the colored balls example. You have a probability that the first ball will be green and the probability the second ball will be green. Now, how are they different? Well, they're different in that, well, when I roll the dice, what I get on the first dice is not going to affect what I get on the second dice. But if you look at the second example, there's a key phrase, without replacing the first ball, which means that when I choose a ball from the first ball from the pile, the probability of whatever I'm choosing the second is going to be affected by that. So this is where we get into stuff like independent events versus dependent events, right? So the dice problem in the previous slide have events that are independent, right? So 2 events are independent if the occurrence or not occurrence of one event doesn't change the probability that the other event will occur, right? But if it does, they're called dependent events. Okay, so 2 events are independent if one event occurring doesn't affect the probability of the other. But if one event does affect the probability of the other, those events are dependent. So although the dice and colored ball examples look for probabilities of more than one event occurring, the first dice roll didn't affect the second. But it wasn't the case in the colored ball example, because when you pull one ball out of the pile without replacing it, there are less balls to pull from, meaning that your sample space is a little bit smaller, affecting the probability of the second pull. Okay, so when we talk about 2 events A and B, and we're trying to compute the probability of A and B, we use multiplication. So here's the multiplication rule if 2 events are independent, right? All you're doing is you're calculating the probability of A times the probability of B. This is for an and probability, okay? And sometimes if the events are dependent, then we have to take into account the changes in the probability of one event caused by the occurrence of the other event. This is called A given B. It's known as conditional probability, where we have to calculate the probability of B, or if we're specifically talking about the probability of A given that B has already happened, we have to consider the probability that A will occur knowing already that B has occurred. This is conditional probability. So the general multiplication, the simple multiplication rule only works for independent events. But if events are dependent, we have to consider that conditional probability here. So this is how the notation is given. So we first off read that as P of A given B is the probability of A given that B has happened. And if A and B are independent events, then the probability of A is not equal to the probability of A given that B. Because they're dependent events, the occurrence of B has changed the probability that the event A will happen. And here's your notation, right? It's P of A with a vertical line down and B. So that's A given B here. All right. So in general, there's a general rule for multiplication, right? The probability of A and B is given by the probability of A times the probability of B given A. And the probability of A and B, is for the other way around too. Now, the reason why this is the general rule is that if the events are dependent, then this here is going to have a different probability than P of B, right? But if they are independent, then this right here, this value here is going to be the same as the probability of B, simply because that the probability of A already happening doesn't affect the probability of B happening. So in that case, they would be the same. Now, depending on what information that we have to use one of these formulas when computing the probability of dependent events. So we first off have to know what A and B are. We have to know if they're independent or dependent. And if they're dependent, then we have to look at, okay, well, what does the probability of B look like if A already happens? Okay, so these three rules help us compute the probability of events happening together when the sample space is either too large or it's not completely known. That doesn't mean we can't use the sample space, but it's an easier way to do it without using the sample space, right? So if we want to calculate probability of A and B, let's say we want to find the probability of B times the probability of A given B. Well, if I solve this by dividing both sides by the probability of B, then I get a formula for that conditional probability here. Okay, so when I have that probability for conditional probability, actually, let me go back. So if I divide both sides by the probability of B, I end up with a formula for finding that conditional probability. Probability of A given B being equal to that probability of A and B divided by the probability of B. Okay. Now, let's go back to the dice example. Let's say that I'm looking for the probability of 5 on each die. Well, the roll of the second die doesn't affect the roll of the first die, so that means that they're independent, right? So the probability of getting a 5 on the first die is the same as the probability of getting a 5 on the second die. And there are 6 faces on the die, right, 1 through 6. So the probability of a 5 on any of those die is 1 out of 6. So if I look for the probability of getting a 5 and a 5, then that's the probability of the first die times the probability of the second die. 1 over 6 times 1 over 6, which is 1 over 36, right? If I were to put that in decimal, 1 over 36, that's about 0.03. Okay. If I look at the sample space, if I look at the sample space here, here's the list of all possible scenarios for rolling the first and the second die. Notice that there's only one instance where I get both 5s, and there are 1, 2, 3, 4, 5, 6 columns. 1, 2, 3, 4, 5, 6 rows. That's 36 total scenarios. 1 out of 36. It's the same. So again, it's not impossible to use the sample space, but if you already know that the events are independent, sometimes it's easier to use the multiplication rule. But now let's go back to the dependent events. Consider a collection of 6 balls that are identical except in color. You have 3 green balls, 2 blue balls, and 1 red ball. Compute the probability of drawing 2 green balls from the collection if the first ball is not replaced before the second ball is drawn. Well, if I'm drawing the first ball, that's 1 out of 6, right? That's one. Well, actually, I have 2 green balls out of 6 that I could possibly draw from, right? So that's probability of the first one being green. That's 2 out of 6, which is 1/3. Now, if I draw a second one without replacing the first one, so, and let's say that I do draw the first ball being green. If I draw a green ball the first time, then that means I have not only one less green ball, which, I need to fix this because this actually should be 3 green balls, because we have 3 and not 2. So now the only thing with that is when I draw a green ball the first time, not only do I have one less green ball to draw from, I have one less ball period to choose from. So the probability of the second is being green, we have to take that into account. So now I have 2 green balls left out of 5. So, and that's because drawing the first green ball out of the pile affects the probability of drawing the second green ball. Okay? So if I wanted to do the probability of both of these, first and second being green, then I multiply these two together. 1/2 times 2/5, right? That's 1/5, which is about a probability of 0.2. So in a general sense, here's how you should use the multiplication rules for and probabilities. So first you want to determine if the 2 events are independent. If one of them does not affect the probability of the other, they're considered independent. If that's the case, then the conditional probability of A given B is the exact same as the probability of A. So that means that they are independent. So if they are independent, then you just simply multiply the individual probabilities together. But if they are dependent, then we do have to consider the conditional probability. So the probability of the first event times the probability of the second event, given that the first has happened. Or the opposite, the probability of the second event given, or times the probability of the first, given that the second event has already happened, depending on what's A and what's B. And that one, for this step here, it's probably a better suggestion to use the sample space to help you out if you can use the sample space. But again, it's because this right here is equivalent to this if they're independent, which is why the more specific multiplication rule is sometimes a little bit more useful, especially if events are independent. Now, can the multiplication rule work for more than 2 independent events? Of course it can, right? For instance, if the probability that a single seed will germinate is 0.85 and you plant 3 seeds, well, assuming that all that's independent, well, we just multiply all 3 of those together, right? So that would be this up here, 0.85 times 0.85 times 0.85, right? And multiply all that together. And if I rounded that to 3 decimal places, that would be about 0.61. Right? So now we'll talk about addition rules. So the multiplication rules can be used anytime we're trying to find the probability of 2 events happening together. So here I have a Venn diagram, and essentially this is the visualization of what we're looking at whenever we're trying to find the probability of an AND event, right? We're trying to find this probability right here, okay? And within our so here's our sample space. Here's event A, here's event B, and here's the event of A and B happening together, okay? But another way to combine events or to use compound events is to consider the possibility of one event or another event occurring, okay? Again, here's what this looks like. The shaded portion represents the outcome satisfying the OR condition. Now, notice that the middle is also shaded too, because if you're looking at event A or event B, if both of them both of them occur, it still counts as A or B because at least one of them happened. But when we look for probabilities like this, especially if we look at it in this context, we see some overlap here, which means certain probabilities are counted twice. So we got to be careful about how events A and B happen, and that's where we run into something called mutually exclusive events, right? Two events are mutually exclusive, or another word is disjoint, if they cannot occur together. In particular, events A and B are mutually exclusive if the probability of A and B is 0. Going back to the Venn diagram, if A and B are mutually exclusive, then this overlap here is not filled in. It's just the outside of A here, the outside of B here. So that's what it means for two sets to be disjoint, is if there's no overlap. Okay, if two events are mutually exclusive, then we're looking for the probability of A or B happening as the sum of the probability of A plus the probability of B. So with AND events, we use the multiplication rules. With OR events, we used addition rules. Okay, and of course, for events that are not mutually exclusive, we use the more general formula, right? If to find the probability of A or B, again, it's the same addition rule, probability of A plus the probability of B, but then you subtract the probability of A and B. And again, going back to the Venn diagram, by subtracting this, we eliminate anything being counted twice, right? I'll write it out here so you can see it a little bit better, right? The probability of A or B, that's the probability of A plus the probability of B minus the probability of A and B. Okay. Now, in order for this to happen, if the events are mutually exclusive, then this area is blank. There is no probability of A and B. That would be 0, which is why you have the simplified, the more specific addition rule. But if they're not mutually exclusive, then we want to eliminate any overlap, because if I add these two together, what I'm doing is I'm adding this twice. This probability of A and B being subtracted from it eliminates one of those instances so that it's only counted once and not twice. Okay, so using the addition rules is similar to using the multiplication rules. First, we have to find out whether A and B are mutually exclusive, and if the probability of A and B cannot happen, if that probability is 0, then those events are mutually exclusive. And again, another way to look at mutually exclusive events is, can both things happen at the same time in the same space? If they are mutually exclusive, if that's the case, then we just use the simplified addition rule. But if not, then we got to make sure to subtract the probability of A and B. Okay, so here's a table, right? An example table. Consider an introductory statistics class with 31 students. The students range from freshmen through seniors. Some students are male, some students are female. Okay. Suppose we select one student at random from the class. Find the probability that the student is either a freshman or a sophomore. Well, the question is, to find out if events are mutually exclusive, we have to ask ourselves, can a student be a freshman and a sophomore at the same time? Well, the answer to that question is no, they cannot. So those are mutually exclusive events, right? So we can easily find that probability by using the specific addition rule. Probability of freshman plus the probability of a sophomore, right? So 31 students in total, so there's 15 freshmen, 15 over 31, plus 8 sophomores, 8 over 31. That's 23 over 31, which again, rounding to 2 decimal places, that's 0.74. Okay. Select one student at random from the class. What is the probability that the student is either a male or a sophomore? Well, Question being is, can a student be a male and a sophomore at the same time? In this case, the answer is yes. So this is where we use the more general addition rule. So that's probability of male plus the probability of sophomore plus the probability of both, right? Male and sophomore. I mean, sorry, not plus. This should be a minus. Let's take that off and put a minus there. This is male and sophomore. Okay, so how many males do we have? Well, we have 6 here, 5, that's 11, 12, 13, 14. So that's 14 over 31. Plus the sophomores, we have 8 sophomores, minus the men that are sophomores. There are 5 of them. So that's 5 out of 31. Okay, so 14 plus 8, that's 22. 22 minus 5, that is 17. That's 17 out of 31, which is 0.55. Okay. So again, in order to find mutually exclusive or to determine whether events are mutually exclusive, you have to ask yourself, can these two things happen in the same space? If they can, they are mutually exclusive. Okay. Now, if two events are mutually exclusive, then we know that the occurrence of one of the events means that the other event will not happen, right? Which means that the and probability of those two events is going to be 0. And of course, in this case, that's where we use the specific addition rule. But it also means that the given probability of A given B is 0, and vice versa. B given A is also 0, because again, they can't happen in the same space. So if events are mutually exclusive, that means that the conditional probabilities are going to be 0, right? In other words, if B occurs, then we know for sure that A will not occur, and vice versa. Okay. Here's another example. It says Laura is playing Monopoly. On her next move, she needs to throw a sum bigger than 8 on the 2 dice in order to land on her own property and pass go. What is the probability that Laura will roll a sum bigger than 8? Oops, sorry. So let's find out. Now, when we roll a sum bigger than 8, right? So that means that I have many choices, right? I have I'm trying to find values of a dice that are larger than 8. So you throw 2 dice. There are 36 total possibilities, right? So for a sum that's bigger than 8, right? That's either a 5 and a 4, a 4 and a 5, a 3 and a 6. Actually, before we do it, we're looking for sums bigger than 8. That means 8, oh, I'm sorry, not 8, 9, 10, 11, 12. Well, to get a sum of 12, you just need 2 6s. For 11, you need 5 and 6 or 6 and 5. For a 10, you need a few more of these. You need 4 and 6, 5 and 5, 6 and 4. And then for a sum of 9, that's 3 and 6, 4 and 5, 5 and 4, and 6 and 3. Right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the probability that Laura will roll a sum bigger than 8? So any of these out of 36, right? So this is one where maybe a sample space would probably be a little bit easier to utilize. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 out of 36, which is about 0.28, probability of 0.28. Okay. Okay. Now let's go to a couple of visual instances of using these rules called contingency table. So contingency table is a simple tally, is a table that shows a simple tally survey consisting of questions to which the responses can be recorded in its rows and columns. So in a contingency table, questions are appropriate to the information you want and are designed to cover the entire population of interest. And they're also designed so that you can partition off the sample space of responses into distinct or mutually exclusive sectors. So here's an example. At Hopewell, all 140 employees were asked about their political affiliations. The employees were grouped by the type of work, executives or production workers. So here's the contingency table. You have employee types, you have political affiliations, and then you have totals for the row and totals for the column, and then you have your grand total here in the corner. Okay, so we're going to use this table to answer the following probability questions. Here's a contingency table for employee type and political affiliation. I want to compute the probability that the person I choose at random is a Democrat and the probability that the person I choose is an executive. Now, this isn't an and probability where I'm finding the probability of two events happening one after, like at the same time. What I'm doing is I'm finding probabilities of separate events. Okay, so the probability that I choose a Democrat at random. So how many Democrats do I have? Well, let's hear at the top. Here, that's this total here at the bottom, 68. Out of how many people? Grand total of 140. Right? So I calculate that. That comes out to about 68 divided by 140. That's about 0.49. Now, if I want to find the probability that someone is an executive, well, here's my executive. How many executives do I have? If I look at this total, it's 48. So that's 48 out of 140, which is about 0.34. So those are two separate probabilities that I found. Now, next example here being the probability of D given E. The probability that the person I choose is a Democrat, given that they are already an executive. Well, if you go back to that formula that we talked about with conditional probability, right? We said that the probability of A and B was the probability of A times the probability of B times the probability of A given B. Or no, I'm sorry. That's the different one. The probability of A times the probability of B given A, right? And that if I wanted to find that conditional probability, find the value of this, well, I would divide both sides by the probability of A, right? Okay, so if I wanted to find the probability of a Democrat, given that they're already an executive, I just switch B and A with D and E. So the probability of, so what I'm really doing is calculating the probability of A and B, or in this case, D and E, divided by the probability of E. Okay? Because that's what I'm looking for. If I switch this out with D and E, that's what I'm looking for. Okay? So if I want to find the probability that someone is a Democrat and an executive, well, how many of them is that? Well, here's a Democrat here. Here is the Democrats that are executives. That's 5, right? So that's 5 out of 140 divided by just the probability that I have a executive, which I already calculated earlier, 48 out of 140, right? Now, whenever you divide fractions, of course, you take the first fraction, multiply it by the reciprocal of the second fraction. So that's 5 out of 48. Well, what's the 48? It's the number of total executives I already have. Okay, so if I calculate that, 5 divided by 48, I get 0.1. There's my conditional probability. Now, are those events D and E independent? So remember, in order for them to be independent, right, the probability of A given B has to be equivalent to the probability of A, right? So the probability of a Democrat given an executive has to be equal to the probability of the Democrat. Well, this is the probability of the Democrat here. Here's my conditional probability that we calculated earlier. Those are not the same. If they were the same, then they would be independent, but it's not. The events are not independent. So knowing that, let's calculate that and probability again by using these two probabilities, right? Using the independent rule, right? P of D times P of E. So that's 0.49 times 0.34. I end up with, or if I do the fraction 68 over 140 times, actually, hold on. I'm not using the specific, I'm using the general rule. D times the probability of, actually, you know what? Probability of E times the probability of D given E. And I already have those, right? That's this 0.34 times 0.1. And I end up with 0.03, which again is what I got earlier, right? At 5 out of 140. So sometimes the contingency table can come in handy. Sometimes that contingency table can come in handy if you want to find and probabilities or probabilities of that for that nature. What about computing the probability of D or E? Well, so D or E, if you recall, is a case where we have to consider whether or not those events are mutually exclusive. So can somebody be on this table be a Democrat and an executive at the same time? The answer for that is yes. That's what this is for right here. So the question being is, so now we know that they're not mutually exclusive, right? So because of that, we have to make sure to calculate the probability of D plus the probability of E. But then we have to subtract the probability of both, so that we don't encounter that double counting that we talked about. Okay, so probability of a Democrat, that's 5 out of 140. No, I'm sorry, not 5, because remember I got to look at the totals. 68 out of 140 plus executives, that's 48 out of 140, minus both Democrat and executive, 5 out of 140. So 68 and 48, that's 116. Minus 5 is 111. So 111 over 140, that's 0.79. All right. Now, last thing I want to talk about is Venn diagrams. We all know how Venn diagrams work. You have two sets. The middle is where both sets have in common. Everything outside of that is where they don't have in common. Okay, so for example, if I were to create a Venn diagram of people who play tennis and soccer, we'll have one circle here, one circle here. This will be tennis. This will be soccer. And if I were to put people in categories, right, I can see that these two people, Casey and Drew, both play tennis, so I'll put them in the overlap. And then Jade plays tennis only. The other two, Brandon and Lance, play soccer. Okay, again, that's an example of a Venn diagram. Now, can Venn diagrams apply to more than two categories? Yes. Let's look at that with this example. So I have people who like cats, I have people who like dogs, I have people who like birds, right? So here's 2 and here's 3. We'll say this is cats. We'll say this is, I'll let that one be dogs. All right. And let's say that I have 10 students who like cats and birds, but not dogs. So I need to find where cats and birds overlap, but not dogs. So that's 10 here. 6 students like cats and dogs, but not birds. So we'll put that here. How many students like dogs and birds, but not cats? That's 2. I have 2 students that like all 3 pets, and then I have the individual cases. 10 like cats only, 9 like dogs only, 1 likes birds only. Now, the only thing is when you look for probabilities based off of that, we got to be careful on how the probability is worded. If I was looking for probability of someone who likes cats, well, I can't just include this number here. I also got to include these numbers because as long as they like cats, they can be included in that list. That's 20, 22, 28 people out of 40, right? But if I were to say cats only, then I can be more specific and focus on everything here, okay? Or if I say how many students like more than 1 pet, well then that means I have to include all 4 of these regions here. That'll be about 20 out of 40 people, okay? Now if I added up all of the responses to the survey, right? If I add up all these numbers, I should get my total number for my sample space 40, being that that's how many total students were surveyed. So we have to be careful on the questions that we're answering. How specific are these questions? If not, how general do we need to be? We have to make sure that we're reading the questions carefully when we're looking for these types of probabilities.